Yeah.
Okay, hi everyone. My name is Kristiaan Neyts. I'm a new professor at Hong Kong University of Science and Technology. So here you see a beautiful view of our main building with the solar indicator. So let me say a few words about my background. I'm from Ghent University originally. I did my PhD there. I was born there in this area. And I've also been at the university in Stuttgart for 1 year, and I've been also at UC Berkeley. Okay, let me show the pointer. Yeah, so that has been my background. And I joined HKUST just in September this year. So I'm very new, I'm very excited. I enjoy the life on the campus. So I think I'm a good example for you. So if you are interested, you can follow me and also join HKUST. I'm not only a professor at HKUST, I'm also the director of the State Key Lab for Advanced Displays and Optoelectronics Technologies. So let me explain a little bit of the things that are done in the State Key Lab. So we know the main types of displays around are the organic LEDs and the liquid crystal displays. And just to make sure that you see a connection with real life, let me explain something about the OLEDs that might catch your interest. So OLEDs, they are just diodes, and they inject holes and electrons, and then they emit light from a central layer. And the optics is also important in such a component. So the optics is done by a dipole antenna, like you have experience with that in your undergraduate studies. And if you have a dipole antenna and you put it in the neighborhood of a mirror, then you have some interference between directly emitted light and also reflection from the mirror. In addition, you also have total internal reflection. This is a view from in the swimming pool, and you see that a lot of light is internally reflected from the surface of the swimming pool. So these are important effects. So if you want to make a good OLED, it's important that your dipole antenna is oriented horizontally, because in that case, most of the light will be emitted towards the viewer. If your dipole, on the other hand, is vertical, then most of the light will be wave-guided and lost for the viewers. So it's important to choose a good material, good molecules to do that. So here I illustrate the effect of the light emission in one direction and also light emission in the opposite direction, which is reflected on the surface of a metal mirror. And these two can interfere. So even if one photon is emitted, the quantum effects make an interference effect for a single photon. And that's important for the application. So nowadays, people always use OLED devices in this case where they choose the distance from the mirror correctly so that you have a lot of emission into air. If you choose a point here with a distance from the mirror which is too small, then most of the light is just emitted into the glass and is wave-guided, and there's almost no emission in the air. So it's very important, and we need engineers to improve the quality of organic LEDs. Another important device, of course, is the liquid crystal display. And in such a display, you have organic molecules which are oriented mainly parallel to each other. So here you see one molecule, and here you see many molecules. They like to be parallel to each other, but you can also stretch them or bend them or splay them, as is illustrated here, and this requires some energy. Now, at HKUST, there is an experience with this material, SD1, and you can use that material to define how you align the liquid crystal. So if you illuminate the substrate with linearly polarized light, you can define how the molecules will orient. It will be perpendicular to the linear polarization. And afterward, if you put the liquid crystals on top, they will follow that alignment. Now, if you align with complex shapes of light, for example, two laser beams which are circularly polarized, then you can create patterns which are very complex and also can have a very short pitch. So you can make a grating of which the period here is on the order of a few hundred nanometers. And you can also make a setup. You can also use a kind of display to project onto a substrate and make complex patterns. And here I show you just a few patterns. So we have made ring patterns which are nicely visible in the microscope. We can also use chiral liquid crystal. If you add some chiral dopants, this material can change and form a helix. It's a bit similar to the DNA helix. And the period can be chosen, if you have the values right, can be chosen in such a way that light is reflected on this helix. And then you create, in fact, a very good mirror. So with such a mirror, if you have two mirrors, a mirror here and a mirror here, and in between you put some luminescent material, you can make a photoluminescent laser. And for that, we have used quantum dots. And I think my colleague, Professor Srivastava, will tell you more about that. So then you can make lasing if you excite it. So you can see very strong laser pulse. And you can also make it flexible. You can bend it, you can put it underwater, and it can still show lasing. If you use the chiral liquid crystal, instead of having just a mirror, which is a flat mirror, you can also orient this mirror. So if you use this principle of variable orientation, you can make the mirror tilted. And that gives opportunity to make complex optical devices like lenses or gratings or all kinds of devices. And this is useful for augmented reality. So many big companies are developing augmented reality. So it means it's the glasses, you can see through them, but at the same time, you can also see information from the display. So it's a very active research field. And so we are working on this. We are trying to improve the quality and couple light from a display into a waveguide and then couple it out so the eye can see the display. But at the same time, because this component is semi-transparent, you can also see the real world. So if you are interested in this kind of topics, I invite you to contact me, to contact people at HKUST, the ECE department. We are all enthusiastic about new research, and we would be happy to welcome you on our campus. Thank you very much for your interest, and hope to hear from you soon.